On the 14th of November 2023, a radio dish in the Mojave Desert locked onto a signal that had been traveling for almost 22 and a half hours. It was coming from Voyager 1, then more than 15 billion miles from Earth. And it should have carried the spacecraft's usual report on its own health and the faint physics of the space around it. Instead, the engineers at NASA's Jet Propulsion Laboratory watched a single repeating pattern scroll across their screens, over and over saying nothing. The spacecraft was still there. It was still listening. It answered every command it was sent. It had simply lost the ability to say anything that made sense, like a person who can hear you perfectly but can no longer form a sentence in reply. That is not, strictly speaking, a signal from somewhere NASA never expected. It's something rarer, and once you understand what was actually happening 46 years into this mission, considerably stranger. The real surprise in the Voyager 1 story isn't a message from an unexpected place. It's that the faint, almost accidental signal this ancient machine has been sending back for the last several years turned out to be evidence of something researchers didn't think they'd ever be able to measure directly, coming from a region of space no spacecraft had ever occupied before, using a method nobody had planned for when the mission launched. To understand why that matters, you have to go back to where this signal even comes from, and how close NASA came to losing the ability to hear it at all. Voyager 1 left Cape Canaveral on September 5, 1977, 16 days after its twin, Voyager 2, launched on a slower trajectory toward the outer planets. It carried a gold-plated copper disc bolted to its side. The Golden Record, assembled by a team led by Carl Sagan, holding greetings in 55 languages, recordings of wind and thunder and whale song, 90 minutes of music from Bach to Chuck Berry, and a diagram showing the position of Earth relative to 14 pulsars, in case whoever or whatever eventually found the spacecraft wanted to know where it came from. Voyager 1 was never designed to be the record holder it became. Its original assignment was a grand tour of 2 planets. It flew past Jupiter in March 1979, returning the first close images of the Great Red Spot and discovering active volcanoes on the moon Io, something nobody had detected on a world other than Earth before. It reached Saturn in November 1980, threading close enough to the rings and to the moon Titan that mission planners deliberately steered it out of the plane of the solar system to get the shot. A decision that ended any chance of a further planetary flyby, but set up the trajectory the spacecraft has followed ever since, climbing outward at roughly 17 kilometers per second relative to the Sun. Voyager 1's brief planetary tour left behind a list of firsts that still shapes planetary science today. At Jupiter, its cameras caught a thin, dark ring circling the planet that nobody had confirmed from Earth-based telescopes, and the discovery of active volcanism on Io, spotted almost by accident in a navigation image meant to pin down the moon's position against background stars, turned out to be one of the most significant single findings of the entire mission. Proof that a small, rocky world squeezed by the gravity of a giant planet could generate its own violent internal heat. At Saturn, Voyager 1 returned the first detailed look at the braided, twisted structure of the F-ring and confirmed that Titan's atmosphere was thick, orange, and almost entirely opaque to visible light, a result that quietly set the stage for the Cassini-Huygens mission 2 decades later. None of that was the deep space physics the spacecraft would eventually become famous for. It was old-fashioned planetary reconnaissance, done with cameras and instruments that were cutting edge for 1977 and would look primitive within a decade. The deep space chapter of the story only began once the planets were behind it, and there was nothing left to do but keep flying outward and see what the instruments picked up along the way. For 3 decades after Saturn, Voyager 1 kept flying through territory nobody had planned for its primary mission, gradually leaving instruments switched off to save power, until in August 2012, its instruments recorded something nobody could have scripted in advance. The density of charged particles around the spacecraft jumped by a factor of 40 in a matter of days. The direction of the magnetic field around it barely changed at all. Together, that combination told the Voyager team that the spacecraft had crossed the heliopause, the boundary where the solar wind, the outward rush of particles from the sun, finally gives way to the thin, cold plasma that fills the space between stars. Voyager 1 had become the first human-made object to leave the bubble the sun carves out around itself and enter interstellar space, a fact confirmed in a 2013 paper in the journal Science, led by Donald Gurnett of the University of Iowa, the longtime principal investigator on the spacecraft's plasma wave instrument, who had waited years for exactly this kind of unambiguous signature to show up in the data. Gurnett's team didn't catch the crossing in real time. They caught it because a solar eruption, arriving at the spacecraft months after leaving the sun, rang the surrounding interstellar plasma like a bell, and the ringing let them calculate its density directly for the first time. That was how the plasma wave instrument was originally expected to work out there, waiting for the sun to provide an occasional, violent, useful disturbance. If you want to know when we're actually going to talk about this channel and what's coming, this is a good place to hit subscribe. Because the part of the story where an old spacecraft did something nobody expected it to do is still ahead of us. And it starts with an instrument that was never supposed to work the way it ended up working. For years after the 2012 heliopause crossing, that dependence on solar shocks was simply how researchers studied the plasma around Voyager 1. No shock, no data point. The interstellar medium is close to a vacuum, and its own natural oscillations are so weak that the instrument needed the plasma to be excited by something bigger before it could register anything at all. Then, starting around 2017, something changed in the instrument's readings that had nothing to do with the sun. A faint, narrowband hum began to show up in the plasma wave data, persistent, monotone, and completely unconnected to any solar event reaching the spacecraft. Stella Koch Ocker, at the time a doctoral student in astronomy at Cornell University, was the one who first noticed it sitting in the data and couldn't immediately explain it. "This plasma line was unlike anything I'd seen before," she would later write, describing it as extremely narrowband and so weak it was only detectable in the gaps between the solar-triggered events the team usually relied on. Uncertain whether she was looking at a real signal or an artifact of the instrument itself, Ocker brought it to Donald Gurnett and William Kurth, the plasma wave instrument's principal investigator and co-investigator, both at the University of Iowa, who ran independent checks against their own long archive of Voyager data and confirmed it wasn't noise. What Ocker had found was a continuous emission that let the team trace the density of the interstellar medium steadily, without waiting for the sun to cooperate, at a spatial resolution finer than anything the shock-based method had ever achieved. The team, led by Ocker, along with Cornell astronomers James Cords and Shami Chatterjee, published the discovery in May 2021 in the journal Nature Astronomy, under the title Persistent Plasma Waves in Interstellar Space Detected by Voyager 1, with Gurnett, Kurth, and University of Iowa, physics professor Stephen Spangler as co-authors. According to Cornell University's own account of the research, released alongside the paper, the finding meant scientists could now measure the density of the local interstellar medium continuously, over spans approaching 10 astronomical units, rather than relying on the rare, discrete plasma oscillation events that solar shocks had previously provided. Chatterjee described the shift in blunt terms and comments reported at the time, saying the team no longer needed a fortuitous event connected to the sun to measure interstellar plasma, because Voyager, regardless of what the sun happened to be doing, was continuously reporting the density it was moving through, over and over, for as long as the spacecraft kept transmitting. That is the unexpected signal underneath the Voyager 1 story. It isn't a message. It's a machine designed in the early 1970s, intended to study planets it flew past decades ago, quietly picking up the ambient hum of the galaxy in a region of space it was never built to survive in. Using a detection method its own instrument team hadn't anticipated using this way when they built it. There is genuine scientific disagreement buried inside that discovery, and it's worth sitting with, because it's the kind of detail a fabricated story would never include. The Nature Astronomy paper itself is careful to note that the physical origin of the persistent hum isn't fully settled. One possibility the authors raise is that superthermal electrons, born either inside the heliosphere or generated near the heliopause itself, are driving the oscillation. Another is that an anisotropy in low-energy cosmic rays, possibly linked to a nearby star, could be exciting the plasma into this steady state. The paper doesn't resolve which explanation is correct, and as of the most recent published analyses, researchers are still working through the implications, because a signal like this, faint enough to sit at the edge of detectability, resists easy interpretation even once you're confident it's real. What the disagreement actually confirms is that Voyager 1 produces for one-handed astronomers a genuinely new kind of data, the kind that raises more precise questions rather than closing the book on old ones. Confirming the density gradient of the nearby interstellar medium isn't a footnote. It shapes how researchers model the size and structure of the heliosphere itself, the bubble that has sheltered every planet in the solar system, including Earth, from a much harsher galactic environment for 4.5 billion years. A denser or more turbulent local medium changes how far out that bubble can push against the pressure of the galaxy, which in turn changes how much cosmic radiation reaches the inner solar system, a question with implications well beyond pure curiosity. Since galactic cosmic rays are one of the practical hazards any future crewed mission deep into the outer solar system would eventually have to contend with. The 2013 science paper from Gurnett's team had already shown that Voyager 1 was sitting in interstellar plasma. What the 2021 Nature Astronomy result added was a way to keep measuring that plasma continuously, turning a single boundary crossing event into an ongoing survey, and surveys are what let researchers build actual maps instead of single data points. It's also worth being clear about what the persistent hum is not. It isn't a radio transmission carrying information, and it isn't evidence of anything artificial. Plasma waves of this kind are a natural physical process, oscillations in charged particles that any sufficiently sensitive instrument sitting in that environment would pick up, the interstellar equivalent of background hiss from a gas that's been gently disturbed. The word hum, which several researchers reached for when describing it publicly, is a metaphor, not a description of an actual sound. Voyager 1's instruments don't detect audio. The plasma wave system measures oscillations in the electric field around the spacecraft and converts them into a frequency the team can analyze, and only afterward does anyone translate that into something as evocative and as easy to overstate as a hum from beyond the edge of the solar system. None of that continuous listening was guaranteed to keep happening, and 18 months after the Nature Astronomy paper appeared, it very nearly stopped for good. That brings the story back to November 14th, 2023, and the gibberish. For 5 months, Voyager 1 kept transmitting its steady, ever-present radio carrier signal, the electromagnetic equivalent of a dial tone, while the actual content behind it stayed locked in a repeating, meaningless pattern. According to NASA's Jet Propulsion Laboratory, the mission team spent that time working almost blind, since the very data stream that would normally tell them what was wrong was itself the thing that had broken. In March 2024, the team sent what engineers on the project called a poke command, prompting the Flight Data Subsystem, one of Voyager 1's 3 onboard computers, and the one responsible for packaging science and engineering data before transmission, to read out the entire contents of its own memory. Linda Spilker, the mission's project scientist, later described to IEEE Spectrum how that readout finally gave the team something to work with. A deep space network engineer decoded the returning signal and confirmed that roughly 3% of the Flight Data Subsystem's memory had been corrupted. A single chip, storing a 256-bit section of memory that happened to include some of the subsystem's own operating code, had failed, most likely, the team believed, from the slow accumulation of radiation damage or simple wear after 46 years in space, though a stray cosmic ray strike couldn't be ruled out either. Here's where the numbers get almost absurd if you actually sit with them. Voyager 1's Flight Data Subsystem has a total of roughly 63 kilobytes of memory and processes about 8,000 instructions per second. A single modern smartphone processes something in the neighborhood of 100 billion instructions per second. The engineers weren't just working across a distance of more than 24 billion kilometers, requiring nearly 22.5 hours for a radio signal to make the one-way trip. They were also debugging a computer with less processing power than a musical greeting card, built by General Electric using components that had been obsolete for decades, with no manual to consult beyond documentation written by engineers who, in most cases, had long since retired. Spilker put the core engineering challenge plainly. The size of the memory was the biggest obstacle in the entire anomaly, because the corrupted code couldn't simply be moved to one empty spot. No single unused block was large enough to hold it. The only option left was to break the affected code into smaller sections, find scattered pockets of free memory across the subsystem to hold each piece, and then rewrite every internal cross-reference so the fragments would still function together as one working program, essentially performing surgery on software nobody in the room had written and no one could physically touch. On April 18th, 2024, the team transmitted the first relocated block of code toward the spacecraft. Then they waited. A command sent to Voyager 1 takes close to a full day to arrive, and any reply takes just as long to come back, meaning a single question, and its answer can span nearly 48 hours from the moment the transmission leaves Earth. On April 20th, according to NASA's Jet Propulsion Laboratory, engineering data returned to Earth in a readable format for the first time in 5 months. Members of the Voyager flight team gathered in a conference room at JPL to watch it resolve, and photographs from that day, released by the lab, show them visibly relieved, some smiling. After 5 months of running one of the most delicate remote repairs in the history of spaceflight on a machine most of them will never see in person. By June 2024, all 4 of the spacecraft's remaining science instruments were transmitting usable data again, restoring, for the moment, the very stream that had let Ocker and her colleagues detect the interstellar hum in the first place. The Register, reporting on the recovery a few days after JPL's own announcement, described the spacecraft as having regained its sanity after months of babbling nonsensically. A fair enough summary of what a repeating, contentless data pattern actually looks like to the people whose job is to read it. What none of that early coverage could fully capture, because the team itself was still working through the implications, was how temporary the relief would turn out to be, and how quickly the mission would have to absorb its next setback. The recovery didn't mean Voyager 1 was suddenly healthy in any permanent sense, and the mission has kept treating every additional year as borrowed time ever since. In October 2024, only months after the Flight Data Subsystem crisis was resolved, the spacecraft's X-band radio transmitter shut itself off after tripping one of its own fault protection systems, a safeguard designed to protect the craft from unknown failures by defaulting to a weaker backup signal. Engineers restored the primary transmitter within weeks, but the episode was a reminder of how thin the margins have become. As the spacecraft's plutonium power source continues its slow, physics-mandated decay, the team has had to make increasingly permanent choices about what to keep running. Heaters have been switched off, Entire instruments have gone dark, not because they broke, but because there wasn't enough electricity left to run them alongside everything else. As of the most recent mission updates, Voyager 1 is down to 2 operating science instruments, the magnetometer and the plasma wave subsystem, the very instrument that first caught the interstellar hum back in 2017. NASA's engineering team has said they believe they can keep at least one science instrument functioning into the early 2030s, with basic engineering telemetry, the simple health and status data that isn't science, but keeps the mission alive administratively, potentially continuing until around 2036, when the power source may finally drop below the threshold needed to run the transmitter at all. Before that eventual silence, though, Voyager 1 has one more milestone to pass, and it's arriving soon enough that the mission team has already put a date on it. On November 18th, 2026, at 2:16:07 in the morning Pacific time. According to NASA's own Voyager status page, the spacecraft will be 16,094,799,096 miles from Earth, a distance equal to exactly one light day. The distance light itself, and therefore any radio signal, travels in 24 hours. Voyager 1 will become the first human-made object ever to reach that distance. CNN's coverage of the approaching milestone, published in December 2025, quoted Susie Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, describing what that will actually mean for how the mission operates. If I send a command and say, "Good morning, Voyager 1," at 8 a.m. on a Monday morning, Dodd said, I'm going to get Voyager 1's response back to me on Wednesday morning at approximately 8 a.m. Every exchange with the spacecraft from that point forward will take a minimum of 48 hours round trip, an operational cadence closer to sending letters across an ocean by ship than anything resembling a conversation. Dodd also pointed out a much more immediate vulnerability than distance itself. If the propellant lines that let either Voyager probe keep its antenna pointed at Earth were to freeze, the mission would end immediately, regardless of how much power remained, because a signal that isn't aimed at Earth might as well not exist at all. Distance isn't the only thing straining this link. On the ground, the 70-meter dish at the Deep Space Network's Canberra complex, designated DSS-43, is one of only a handful of antennas on Earth sensitive enough and correctly positioned in the southern hemisphere to communicate with Voyager 1 at all. That dish went offline for major upgrades between May 2025 and February 2026, with only brief operational windows opened in August and December of 2025, and the Voyager team had to plan its communication schedule around a ground station that was itself partially unavailable for the better part of a year. Voyager 2, meanwhile, is tracing its own path out of the solar system on a different trajectory, currently sitting at roughly 19.5 light hours from Earth, close behind its twin, but not on the same schedule to reach the one light day mark. Both spacecraft depend on the same aging network of Earth-based dishes, the same shrinking pool of engineers who still understand 1970s spacecraft architecture well enough to write patches for it, and the same dwindling supply of electricity from radioisotope thermoelectric generators that have been quietly losing about 4 watts of power output every single year since launch, with no way to replace or recharge them ever at any distance. If you've made it this far, you already understand why a channel like this one exists, to take a story with a genuinely wild headline and show you the real sourced version underneath it. And if that's the kind of thing you want more of, this is the moment to subscribe, because the last piece of this particular story is the part that actually answers the question the title is asking. So where does that leave the signal the title promises? The one from somewhere NASA never expected. It was never going to be a message, and no credible source, not NASA, not a peer-reviewed journal, not any of the researchers actually running this mission, has ever claimed otherwise. But the honest version of that headline is still remarkable on its own terms. The signal Voyager 1 has been sending back since 2017 is a continuous, faint hum of interstellar plasma, detected from inside the interstellar medium itself, a region no spacecraft occupied before Voyager 1 crossed into it in 2012, using a detection method the instrument's own team hadn't originally planned on relying on, since it was built to catch rare solar shocks, not steady ambient noise. Nobody expected a 49-year-old spacecraft with 69 kilobytes of memory to become an ongoing observatory for the density structure of the galaxy immediately outside our solar system, and yet, according to Cornell University, the University of Iowa, and the peer-reviewed pages of Nature Astronomy, that is precisely what it has been doing on and off, in between a 5-month communications blackout and a transmitter fault for years now. The spacecraft nearly lost the ability to tell anyone about it in November 2023. It got that ability back in April 2024, through a repair performed at a distance of 24 billion kilometers, on hardware nobody has touched since Jimmy Carter was president. And in November 2026, it will cross a threshold no human-made object has ever reached, becoming, for a little while longer, a light day away, still listening, still reporting on a region of space that 4.5 billion years of Earth's history had never been directly sampled from before Voyager 1 got there. There's a particular kind of asymmetry worth sitting with before this closes out. Everything that made the 2023 breakdown so alarming, and everything that made the 2024 fix so difficult, came down to the same fact. Voyager 1 is simultaneously the most remote piece of engineering humanity has ever built, and one of the most fragile, dependent on decades-old memory chips, propellant lines that cannot be inspected, and a shrinking cadre of specialists who understand hardware. Most engineering schools stopped teaching before some of the current mission staff were born. And yet that same fragile, obsolete machine is the only thing currently capable of handing scientists a direct, continuous physical sample of the interstellar medium, a region that every other instrument humanity has ever built, every telescope, every detector, has only ever been able to study from a distance filtered through the heliosphere's own boundary. Nothing else we've launched has gotten out far enough to matter here. The James Webb Space Telescope can resolve galaxies from the early universe with extraordinary clarity, but it cannot tell you, the way Voyager 1's plasma wave instrument can, what the density of charged particles is doing right now, in situ, 30 astronomical units beyond the edge of the sun's influence. That's not a knock on Webb. It's a reminder that some kinds of data can only come from actually being there, and right now, being there is a 49-year-old spacecraft running on borrowed time and a computer with less memory than a single low-resolution photograph. The golden record is still bolted to the side of the spacecraft, carrying its greetings in 55 languages and its map back to a small planet near an unremarkable star. And it will keep traveling outward long after the last watt of power runs out, and the last signal, sent or received, fades into whatever comes after. That's the actual ending this story is building toward. Not a discovery finished, but a machine that will eventually go quiet mid-sentence, having already told us more about the space beyond our sun than anyone in 1977 had any reason to expect it could. If a headline promising a signal from somewhere unexpected undersold what's actually happening out there, that's rare enough to be worth your attention on its own. And if you want to be here when the light day milestone actually arrives in November, or when the next update on Voyager 1's slow, remarkable decline comes in, subscribing is the way to make sure you don't miss it. Consider what's actually being asked of a piece of 1970s hardware right now. It has to keep its antenna pointed at a planet it left behind. Before most of the people currently operating it were born, keep a plasma wave instrument sensitive enough to register oscillations smaller than any signal its original designers expected to chase, and keep doing all of that on a power budget that only shrinks, never grows, year after year, with no possibility of a resupply mission or a repair crew, ever. Every additional data point Stella Koch Ocker or James Cords or Shami Chatterjee pulls out of that thin stream of numbers is a data point that couldn't have been collected any other way, from any other vantage point, by any other instrument currently in operation anywhere in the solar system. That's what makes the real Voyager 1 story worth telling honestly, without needing to invent a mysterious transmission or an unexpected discovery that never happened. The true version was already strange enough. A machine that was supposed to finish its job at Saturn in 1980 is still in 2026 the single best source humanity has for understanding the plasma physics of the space just outside our own solar system. And it very nearly lost the ability to tell us anything at all, twice, in the space of a single year. It kept going anyway, because a small team of engineers refused to let a stuck bit in a 46-year-old chip be the reason the longest-running conversation in the history of spaceflight finally went silent.